All right, Chapter 10, States of Matter. As you guys know, I'm not going to officially lecture on this. I'm just going to make videos on it. And then we'll have a quiz or a test actually over this, just on the conceptual portion of it. I don't know, probably in a week or so after you guys start watching the videos. Okay, so in section one, the kinetic molecular theory of matter, one of the more important theories that we need to discuss, we're going to take a look at how it applies to gases. So here's the objectives. You need to state the KMT, which stands for the kinetic molecular theory, and describe how it explains certain properties of matter. There are 5 assumptions of kinetic molecular theory as it applies to gases, so make sure you know those. And then you got several properties of gases and ideal conditions for gases, so we'll get into all those. All right, the kinetic molecular theory basically says, in a nutshell, that matter is constantly in motion. Matter is constantly moving, whether it's a solid, liquid, or a gas. Now, what we like to do is talk about the kinetic molecular theory as it applies to gases. Why do we do this? The answer to that is because gases are the most dynamic. Gases are constantly moving. They're always jiggling. They're always turning in space. They're always moving in a three-dimensional pattern. Okay, so gases, if I have an ideal gas, when I talk about ideal gases, an ideal gas is one that fits all 5 assumptions to the kinetic molecular theory. Now, here's the truth of the matter. Not many gases fit all 5 assumptions to the kinetic molecular theory. Many of them deviate in 1 or 2 ways, but sometimes those deviations are so slight that we consider them to be ideal gases and do calculations with them as the ideal gases anyway. Okay? So, the 5 assumptions to the kinetic molecular theory, here are the first 2. All right, the first ones are the first one is pretty simple. Gas particles, if I would consider a gas, a solution, a three-dimensional block or volume of gas, I am going to assume that these gas particles are very small with tremendously large spaces between them in respect to their size. So gas particles are very, very small. The gases are mostly empty space, and we would expect that the volumes are greater than their respective liquids. So if I were to take gases and I were to condense them down to a liquid form, the gas is 1,000 times bigger in volume than it would be as a liquid. Okay, so now this is under same temperatures and pressures and stuff like that. So if I were to have gases condensed down to a liquid under the similar conditions or same conditions, gases would be 1,000 times bigger in three-dimensional volume than their respective liquids would be. Okay, so that's the first assumption. So gas particles are very tiny and they're very far apart relative to their size. All right. Now, the next thing we have is that particle-particle collisions, and according to the kinetic molecular theory, and particle-container collisions are elastic. Now, elastic means that there's no loss of energy. So what that means is this. If I have two cars ramming into each other, we know that they hit and stop. That's an inelastic collision. There is some loss of energy. When 2 gas particles hit, we're going to assume that the energy before the collision and after the collision is going to be the same. So there's no net loss of energy upon collisions. Now we can see this. If you picture a Mylar balloon, which is that shiny stuff, and you know that they fill them with helium, and the Mylar balloon stays inflated for a long, long time. So Mylar must have very small pores, so they're not leaking any of the gas, but the particles actually stay bouncing around. Now, if these particles collisions were inelastic, once they would collide on these many, many collisions, then the balloon would eventually deflate and fall to the ground in a matter of moments. But we see that the balloon stays inflated, so these particle collisions must be elastic. They must not lose energy when they hit. Okay, that's essentially that in a nutshell. Okay, assumption 3, gas particles are in continuous random rapid motion. That's a very simple statement right there. This leads us to different phenomena such as diffusion, but gas particles are always constantly moving, and their motion is random, and it's rapid, and it's always continuous. Number 4, there are no net forces of attraction between gas particles. So as 2 gas particles approach each other, we're saying that an ideal gas, they have no net forces of attraction. They don't attract each other. They're not attracted to each other. Now, I pose a question here in the notes. But what about London dispersion forces? We know that oxygen and nitrogen and chlorine and other gases are all subjected to weak forces of attraction. These weak forces of attraction are called London dispersion forces or van der Waals forces. Now, these London dispersion forces are only between nonpolar substances. Well, oxygen's nonpolar, nitrogen's nonpolar, chlorine's nonpolar. So there is some force of attraction between gas particles, especially in what we call real gases. But this force of attraction is so small, it's so minute, that these particles, these gases, would rather diffuse. Think about it like this. The perfume industry wants you to buy their perfume or their cologne. And imagine if there were strong forces of attraction between perfume or cologne particles, they would stick to you. You want to walk around smelling good and having this cologne and perfume emanating off of you, and therefore other people see you and say, wow, that person is cute because they smell good or whatever. Anyway, the idea behind this is that these gas particles would rather diffuse. If they were to be more attracted to each other, then they would stick to each other and they would never diffuse. So we see that gases diffuse. We see that in point 3 they are in continuous random rapid motion. And because they're in the continuous random rapid motion, we are going to say that there are no net forces of attraction. Okay? I am telling you that there are weak London dispersion forces, but I'm also telling you that they are very weak. Okay? So they don't amount to much. Okay, next. The fifth assumption to the KMT is that the temperature of gases depends on the average kinetic energy of those gases. All right. Temperature and kinetic energy go hand in hand. Okay, you can see that the kinetic energy is 1/2 mv squared. What this is telling us is that the kinetic energy, thus the temperature of the particle, is dependent upon how fast it's moving and its size. So if two gas particles are at the same temperature, they are moving. If one particle has a large mass, you'll notice that if it's 1/2 mv squared, if one particle has a large mass, then it's probably moving pretty slow. And if a particle has a small mass, then it must be moving very quickly, as long as their temperatures or their kinetic energies, let's say temperatures, are equal. Okay, so let me summarize that. Two particles that are moving, that have the same kinetic energy, thus the same temperature, of different sizes, must be moving at different speeds. Okay? Two particles that have the same temperature, thus the same kinetic energy, they are moving at the same speeds, they must have different sizes. Okay? So I just said it two different ways. So as one goes up, the other goes down. All right? Next. All right, states of matter. We're going to talk about this real quickly. You notice that solids and liquids here, they're called condensed states. So solids and liquids are what are called condensed states. These states are ones that the particles stick to each other. Okay, you'll notice that solids holds its shape and has a fixed volume. We're going to get into that. Liquids have a more free, they're more flowing. That's actually called a fluid. Gases are also fluids, but they can explore the three-dimensional shape or container much more than liquids can. All right. KMT theory and the nature of gases. All right, as far as gases goes, we see that they have an indefinite shape and an indefinite volume. Any gas can expand the shape of any container. Okay, they do this because of the random rapid motion, the assumptions 3 and 4. If we take a look back at assumptions 3 and 4, we're taking a look at constant random rapid motion and the fact that they don't have very strong forces of attraction between them. Gases are also fluids. They have the ability to flow. Some gases are dense. They can flow actually downhill. Carbon dioxide is known to be a little bit more dense, and we notice that there is a greater capacity of carbon dioxide in lower elevations, especially lower altitudes. That has to do with molecules move past one another, and that has to do with assumption 4. Gases also have a low density, which is equal to the density of 1/1000th that of their respective liquids and solids. We've already addressed this. That was assumption 1. Next, gases are compressible. With pressure and space between gas particles, they can be, with pressure, the space between gas particles can be significantly decreased. I can squish gases. Why? Because of assumption 1. They are very, very small particles with tremendously large spaces between them, so you can actually compress gases. Um, if we take a look at pressurized methane gas cylinders, we see that they are significantly heavier than empty ones. Or if you take a look at propane tanks, your dad or you probably somebody that you know has a propane barbecue or propane gas grill. And these gas grill tanks are propane, and when they're empty, they're actually not that heavy. When you fill them with propane, you swish it around, you can tell that they're liquid. So that's the first thing that you'll notice. Compressed gases can actually form liquids under high pressures. But second of all, I can compress them down, these gases, to a very small space because of their tremendously large spaces between their very, very finite particles. All right, diffusion and effusion. Diffusion is the spontaneous mixing of two substances due to their random motion. That's assumption 3. And we know that gases diffuse. So if you were in one side of the room, you were to spray some cologne or some perfume, that gas will diffuse so the whole room can smell it. So it diffuses that's a random mixing or spontaneous mixing of two particles. And then we have effusion, which is a little bit different. Effusion is gas particles passing through a tiny opening due to their random motion. And the best case I have for this is a balloon, a latex balloon. And with latex balloons, we see that they diminish in size over time, actually somewhat rapidly, especially if they're filled with helium. The helium particles are actually somewhat slightly smaller than the pores in the latex, and they actually effuse through these small openings. So due to their random motion, assumption 3, they are moving through these small little holes or pores. So effusion is a little bit different than effusion. All right, ideal gases versus real gases. I've touched on this briefly. A real gas is one that deviates from the kinetic molecular theory. All gases are considered to be real gases, and there are some exceptions. Noble gases are some of them. Now, if I can take a gas, a real gas, under high pressure, and again, a real gas is one that deviates from the kinetic molecular theory in some way. But if I can take a real gas and I can make it go very fast, I'm sorry, if I let me reverse that. If I can take the gas and slow it down, so the particles are moving very slow, and I put it under very high pressures, I see that I can have a gas that really deviates from the kinetic molecular theory. Why? If I have high pressures and low temperatures, the particles are moving very slow and they're under extremely high pressure. So they're probably going to be very close to one another. If the gases are moving very close to one another, they probably are exerting or being subjected to greater London dispersion forces. So if I have high pressures and low temperatures, I have more of a real gas. Okay? Now let's take a look at the opposite of that. If I take a gas and move it very fast, I jack up the temperature way, way high, and then I subject it to very, very low pressures, I now have particles that are, number one, they're moving very fast, so they're not really interested in one another. And number two, they're also under extremely low pressure, so they're not really sticking to one another because there's no force that's forcing them to be sticking to one another. So high temperatures and very low pressures gives me the best case where a real gas will become an ideal gas. Okay. Next, the more polar a gas is, the more it is a real gas because of greater London dispersion forces. So the more sticky the gas is, the more polar it is, the more it deviates from being an ideal gas, and the more it's a real gas. The most ideal gases are noble gases. These are very nonpolar. I've already mentioned that, but there it is again. Okay? All right, that ends the first section. I'll move on to the second section shortly.